reminder, the chapter we're doing now is thermodynamics. And thermodynamics is kind of a very basic science that you can use to, if you're a chemist, explain a chemical reaction. You can get mostly products, mostly reactions, some sort of equilibrium mixture. And as you'll see starting Monday probably, you can actually not just say mostly product, but you can say how much. You can say exactly how much you would expect for a given reaction. So kind of leading up to that, and what we've done so far is really just a review of Chapter 6 of thermochemistry, and it's looking at enthalpy and enthalpy changes. Now, the first law of thermodynamics says the simplest form is it's just the law of conservation of energy. So, law of conservation of energy is that applied to chemistry, any chemical reaction, the total energy of the universe doesn't change. So it's more broad than that. It applies to all processes where there is an energy change. Whenever energy goes in here, comes out somewhere else. So total energy of the universe is constant. And you can do some math that really isn't general chemistry level, but it gets into the definition of delta H is Q at constant pressure. So enthalpy change is the heat flow at constant pressure, and that's a consequence of the first law. So the second law of thermodynamics, and there are only three of them, the second law of thermodynamics has to do with entropy. So that's what today's class is about. First part is concept of a spontaneous process. Now, a spontaneous process, if you don't think about it too carefully, it's really easy to define. It's a process that happens by itself. So if I have the chalk up here and I let go, it drops. That's a spontaneous process. Now, you start getting into defining things real carefully, and it gets a little bit trickier. First of all, spontaneous, if you think about it in everyday English, usually means it happens very quickly. It happens all at once, right now. In thermodynamics, it doesn't, the speed is not part of the definition, only that it does happen. Now, when I say this is a spontaneous process, letting it go and it drops, I did have to actually do something to make it drop. I had to let go. And another spontaneous process is burning natural gas, like in the burners in the lab. It just burns with, you don't have to do anything to make it happen on an ongoing basis. But with the burning the gas, when you've been up there, you have to use a striker to get it to go. So the ongoing thing would be, if in order to burn something, you had to keep on pumping in energy to keep it burning all the time, that would not be spontaneous. So if you have to do something to let the chalk go so it'll fall, or ignite the gas so it'll start burning, but then it keeps on going by itself, it's producing its own energy as it goes, then it's a spontaneous process. So a lot of what I'm going to go through today gets back to taking a look at a chemical equation and deciding if that's going to be a spontaneous process or not. Which means, will you produce product if you just maybe have to kick it to get it going, but will it keep on going and produce product without any ongoing input? So the key to this is another thermodynamic function. So enthalpy is the first of the thermodynamic functions, and entropy is the second one. So, H for enthalpy, capital S for entropy, thermodynamic function increases with the number of energetically equivalent Okay, so technical definition here, entropy is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system. You can kind of blur this part out when you're trying to just begin to understand this, and it gets more important later on. Now, the kind of common way to think about entropy is disorder. And I had a very dramatic, for me personally, example of entropy this morning. So you're looking at ways to arrange components of a system. So the system in my office is a lot of papers that are very important to me, including the notes for today's class. And usually I start off in August with everything arranged and pretty clean desk and things in files. And if I need to find something, there's not much entropy. There's only like a couple of ways I can arrange things in my office that make any sense. So by today, if you've been to my office recently, it doesn't look like that at all. I mean, it's mostly, if there's a horizontal surface, it's about this high with papers. So it took me about 15 minutes of trying to find the notes for this class to realize that I couldn't find them anywhere, and the clock was ticking. And I don't know if you guys realize this, but it takes me about an hour to prepare for every hour of lecture I give. And without it, it's not that I don't understand this stuff, I just don't remember how to explain it every time. So I said, I give up. I just started writing down new notes, which would have left out half of the stuff for the lecture, and then said, oh, I put it in my bag to take home. And so I have it there, but that's an example of, over time, the entropy increasing just because there are now probably, if you look at like different positions in the stack of papers, I bet there are 1,000 places that this could have been, and including one that I didn't even realize was a place it could have been in. That is high entropy. Also, it is a natural process to increase entropy as time progresses. Okay, so example of entropy, and then the second law of thermodynamics. And this is my excuse for my office, is that the entropy of the universe increases for every spontaneous process. So it's just natural. Nature always increases entropy. You can make trade-offs. You can kind of slow down the increase of the entropy of the universe, but it just always increases. Okay, so now let me show an example of something besides class notes in an office as an example of changes in entropy. This is the concept problem 18.2, and they're looking for the sign of delta S. So delta S, it's like delta H, it's final minus initial, delta anything. So this is change in entropy. So if the entropy is increasing, then the final value will be bigger than the initial value, and delta S will be positive. And if the entropy is decreasing, then the final will be a lower value, so final minus initial will be less than 2. So I'm going to show 3 sets of problems. And this is kind of a standard way that most textbooks have of looking at ideal gases in different volumes. So you've got the volume of the gases, it's sort of like you have 3 chambers, and they have little tubes connecting them. So you're going to be going from, so think about it as like a chemical reaction. Here's the starting point, here's the finishing point. And I always have to kind of stop and reorient myself when I see these problems every year. But what you're thinking about is basically the dots represent molecules of gas, and the little block things represent containers that the gas is enclosed in. So both of them, you have 6 molecules of gas in the overall volume. Now, in the first one, you have all of the gas restricted to just 2/3 of the total volume. And here the gas is spread out. So it's looking like me looking for my class notes. If I have just 2 piles, it's not too bad. If it's 3 piles, it's worse. So the entropy here is going up because you have your components of your system spread out into 3 places rather than just 2. So the question was, is delta S positive or negative? Answer is delta S is positive. Okay, so B and C, it's the same thing. Instead of trying to draw the little system, just going to erase the gases. And this time it is okay, so this time you can tell me positive or negative. Negative. Yeah, negative. It's just the opposite. In fact, you could even say it's more negative than the first one was positive, because you're going from filling up all 3 to just filling up one of the chambers. And then the last one, just to get the same concept, but looking a little bit different. So here you've got gas in 3, it's going down to 2, so delta S is negative. Now, when you're doing this, there's a tendency to have the mind looking at different things. All that's intended here is you've got 3 locations you can find the gas, how many of them are being used. Okay, so that's the simple one. And that's purely conceptual. But it gives you the basic problem of taking a look at how things are pictured and how that tells you a little bit about their entropy. Now, getting a little bit closer to actual chemistry, changes of state. Oh, I want to look at relative entropies for solid, liquid, and gas. And when you have a solid, and let's make believe it's the same number of particles, you've got a solid here, they're all at the bottom, they're all touching each other, and they're all fixed in position. Now, they might be vibrating back and forth a little bit, but if you go in and mark one of them and then come back an hour later, you'll find it exactly in the same place. So this is very low entropy. Okay, in the liquid, they're also all at the bottom. They're all also in contact. But if you go in and mark one of these, they're free to move around at the bottom of the container. And so you come back an hour later, and you know it's in the bottom of the container, but you have no idea where. So the entropy is going up a little. Okay, and then the gas, you're going to either have to have a bigger container or just a lot of space. But you go in and you mark one of them, and it's no longer an hour later that you know it's at least in the bottom of the container. It could be anywhere. So on this one, the entropy is very high. Okay, so solid, liquid, and gas determines how much entropy you have. Now, in a chemical reaction, and this is kind of a follow-up here, for a chemical reaction, more moles of gas means more entropy. So, same type of problem as the first one. The first one is purely conceptual, and this one is closer to actual chemical reactions. First one is H2O gas condensing to H2O liquid. So, positive or negative? Yeah, gas to liquid, so high to low. The difference is going to be negative. Now, I'm going to put this up the way it was written in the textbook. Solid, carbon dioxide, that's dry ice, sublimes. Now, it's a term, sublimes is a term that you saw very early, like maybe the second week of classes or something, in August. But it means going directly from a solid to a gas. So same compound, solid to gas, entropy, change, positive or negative. Yeah. Okay, and then the third one is an actual chemical reaction. And on this one, again, with chemical reactions, they're tricky. At this stage, all you know is the more moles of gas you have, the higher the entropy. So 2 moles of gas here and 3 moles on the other side. And so it's got to be positive. So again, it's, we'll get a little bit more sophisticated later, but all you're looking at this stage is just moles of gas. If it increases, delta S will be positive. Okay, now, next step in the progression is doing some calculations, and this is kind of the equivalent of the stoichiometry problems with the delta H. So you're looking for different ways to get values for the entropy changes, so you can figure out if something's going to be spontaneous. Okay, so reversible process. Let me start off with one that is not reversible, which would be an explosion. So a chemical explosion, say you have TNT and you set it off and it explodes, it's not reversible. You can't unexplode TNT. The best example of a reversible reaction is if you have ice and water, so ice cubes and water, and you have a kind of heater cooler. So you can turn the heat up a little bit or turn the heat down a little bit, and you have good insulation around it, and you've got your thermometer in there. As long as you have solid and liquid at equilibrium, you're at the melting point or the freezing point. So for ice and water, as long as you have both, as long as it's well insulated, that'll be right at 0 degrees Celsius. Now, if you're in a room, it's going to start melting a little bit if it's a warm room. So you turn the cooler on a little bit, and you can keep it there indefinitely, as long as you put in a little bit heat here, a little bit out. So this is if you want to, say, melt it eventually, you can take as long to melt it as you want. You can take an hour, you can take a week, you can take 20 years if you were patient enough. So that's an example of a reversible process. Usually the examples for a reversible process in chemistry are phase transitions, like the melting. And boiling would also be the same thing. So phase transitions they don't have to be, but they can be done in a slow and controllable manner, so they can be reversible reactions. So, writing it as a chemical reaction, but it's the condensation of water vapor into liquid water, and that's negative 40.7 kilojoules. So it's exothermic when you are condensing it, and this is at the boiling point, at the normal boiling point. So suppose you have 25 grams of water. What is delta S? Okay, so this is kind of like a thermochemistry problem. And it's going to be the same type of unit transition that I've used before. So the heat, you've got, here is your thermodynamic part. So 1 mole of H2O is going to be negative 40.7 kilojoules. So the Q is 25.0 grams of water. You need a molar mass now, so look up oxygen and 2 hydrogens. 18.02 grams equal 1 mole. And then you have this kind of thermochemical mole ratio. 1 mole is negative 40.7 kilojoules. And then calculate that through, and you've got negative 56.5 kilojoules. So the question was, what is delta S? And here you need this definition. This is a phase transition, so it's a reversible process. You just calculated the Q, so it's going to be Q over T. The last part of the definition, I guess I left out here, the temperature needs to be Kelvin. Anytime you're doing a ratio with temperature, you need to have Kelvin in absolute value or Kelvin. So 100 degrees, you add 273.23. And that is finally negative 0.151 kilojoules per Kelvin. So the per Kelvin part is part of any value for an entropy change. And you see that you're getting a number here that's less than 1. Typically, if you look this up or you're trying to find an answer somewhere, that would be converted to joules per Kelvin. So most likely, you'll see it that way. If the problem doesn't specify units, I would just stop there. But if you want to convert, move the decimal 3 to the right, and you get 151 joules per Kelvin. So either one, since it's not specified. Okay, so all of that was kind of practice. Now I'm going to set up the type of problem that this is good for. And that is trying to figure out if a given chemical reaction is spontaneous or not. So, entropy change for the universe. Basically, in chemistry, in thermodynamics, the universe is 2 parts. It's the system, which you're interested in, and it's everything else. So, delta S for the system plus delta S for the surroundings. So if you have special conditions, which are constant temperature and pressure, so it's like a phase change, it's like melting the ice cube, the temperature stays at 0 degrees and the pressure is not changing, then the delta S for the surroundings, and that's pretty much what was going on back here is delta H for the system divided by the Kelvin temperature. And delta S for the system, we don't have a way to calculate that, but we do have a way for deciding whether it's positive or negative. So here's the problem. So first thing is, well, the ultimate thing is to decide whether that's a spontaneous reaction or not. So this is more sneaking in the organic chemistry, but if you're looking at combustion of propane, what you're talking about is burning natural gas. So the question amounts to, does natural gas burn spontaneously or not? And again, there is the part about you do have to set a match to it, but then it burns all by itself. You don't have to keep heating it up to make it keep going. So the answer is going to be yes. And it's kind of good to know the answer going in, because there are a lot of places where one little mistake and everything gets turned around. So first thing, delta S of the surroundings.
Dr. Larrabee, sorry,
Yes.
real quick.
Yeah.
Yes, sign of this, what's yes? I'm sorry.
Is it spontaneous or not?
Oh, is it spontaneous? Okay.
Yes,
Thanks.
it is. Because you know that propane burns.
Okay.
Okay, so first is going to be delta S for the surroundings. Negative delta H for the system over 2. Now, in this problem,